Hi folks, welcome to this video which I'm calling a crash course in rational functions. So rational functions are fractional functions. And a lot of the stuff that we do here is going to have tie-ins for the start of calculus, so it's worth doing. A basic rational looks like this. It's a fractional function. We've seen these before. We called it a hyperbola as its real name, but we had the sort of colloquial name of calling it a butterfly. It has both vertical and horizontal asymptotes. So on this one over here, it would be moved right 2, and its general shape would be something like this. It would go around these asymptotes. And this one would have a vertical asymptote of at x equals 2. You can just see it there. And the horizontal asymptote would be at y equals 0, or the x-axis. So one thing to think about is, why does it have those asymptotes? And I'm going to let you think about that for a little while. I'm not going to deprive you of the joy of discovery. One thing I do want to remind you is that you could find the y-intercept on any function by subbing. Should be another b there. 0 for x. That's how you find a y-intercept easily. In this section, we're going to investigate the behavior of more complicated rationals. And with any luck, we'll discover some rules about their behavior and deepen our understanding of infinity and of division by 0, or at least sort of poke around at those concepts. So what I'd like you to do is pause the video and predict the locations of the vertical asymptotes on these 6 functions. If you have any insight or if you have any guesses, just take a minute or so, think about it, and then we can use Desmos to confirm or dispute our predictions. Okay, so hopefully we've done that. The first one, we really don't need Desmos for. It's going to be moved right 2. It's a basic butterfly. I think that there's going to be a vertical asymptote at x equals 2 on this one. Okay, that's the location of the asymptote. And you might notice that 2 is the number that makes the bottom 0. We can check it out on Desmos. Here's the graph in question. Yeah, at 2 it seems to go off towards infinity or negative infinity, and the graph doesn't actually exist at x equals 2. Let's check out the next one since we're here. Y equals 1 over x squared looks kind of like an Atari symbol. It seems to have a vertical asymptote at x equals 0. Okay, so this one is going to have an x equals 0 vertical asymptote. Let's check out the next one. Oh, wow, that's a weird one. It seems to have 2 vertical asymptotes. One at negative 2 and one at positive 2. And you might start to think, hold on, well, those are just the places that make the bottom 0. Like, in this function over here, you could have factored the bottom and seen that the numbers that zeroed out are 2 and negative 2. In this function over here, well, 0 makes the bottom 0. And in this one, 2 makes the bottom 0. So you might be inclined to conjecture for the next one that you're going to have the same asymptotes as you did for C. But something weird is going to happen. It has one asymptote, and it has it at x equals 2. So the plot thickens. We could play around with this, but let's just keep going. The next one, I guess I could factor the bottom and come up with some guesses. I'm going to guess that the numbers negative 4 and 2 make the bottom 0, so that's where I expect to have asymptotes. Let's see. Yep, asymptotes at x equals negative 4 and at x equals 2. As predicted. So I could do the same thing with this next one. It's got the same bottom, which factors. So I'm going to guess that it has the same vertical asymptotes, the numbers that make the bottom 0. And again here, something weird's going to happen. It only has one of those 2. So the x minus 4 was not true. It's only x equals 2. Maybe this one can help us understand what's going on. If I look at this in its factored form, it factors to x plus 4 and x minus 2. And I guess same with this one over here. We could think of it in its factored form. It becomes x plus 2, x minus 2 on the bottom. The vertical asymptotes are going to come from places that make only the bottom 0. Okay, so in this one, x minus 2 makes only the bottom 0. In all these other ones, these numbers cause the bottom to be 0. But the question is, what's happening around, I'm going to choose a different color, around this point? Like, what is happening at x equals -2? Because you can't put in -2 into this function. And in this function, you can't put in x equals -4. It turns out that the graphs are lying to us just a little bit on Desmos. So let's take a look at this one that has something weird happening to it at -4. Let's see what happens on the graph at -4. Oh my gosh. At -4, it's undefined, and you can see it turns into a little hole there. There's actually a tiny hole in the graph. It's not an asymptote. You might say, well, why doesn't the hole show up when I just look at the graph? That hole is infinitesimally small compared to all of the other points around it. So, I mean, how big a space does it represent? Almost nothing, really. But definitely at that point, the graph can't exist. Same if we think about the sort of fourth one, this one over here. It has a vertical asymptote at x equals 2. What's happening at -2, though, on this one, the other place that makes the bottom 0? You've probably guessed it. Let's see if I can get right on there. Oh my gosh, it's got a hole in the bottom, or a hole in the graph, rather. If we were to generate some rules around this, it seems like numbers that make just the bottom 0 create asymptotes. Numbers that make both the bottom and the top 0 create holes in the graph. So we've got a hole at x equals -2. Graph doesn't exist there. Hole at x equals -4. The last question might be, okay, well, what happens to the numbers that make only the top 0? And the third one, this one here, might be a good one to investigate. So it's x plus 3 all over x squared plus 2x minus 8. -4 and 2 make the bottom 0. -3 makes the top 0. What happens at x is -3? Well, that's where you get an x-intercept. Okay? And that's because it causes the numerator, or the top of the fraction, to be 0, which means that the whole y value is going to be 0, if just the top is 0. Because 0 divided by anything other than 0 is just 0. That'll also happen in the third one here. The number 0 makes the top 0, so that's where your x-intercept is. We can present this information concisely here. When you're analyzing rational functions, factors that only appear on the top are x-intercepts. Factors that only appear on the bottom are vertical asymptotes. And factors that appear on both the top and bottom, they can be divided out, but they represent holes or points of discontinuity on the original graph. And if we want to find the y point, then we have to divide them out. We'll see that as we go through a few examples. But let's just start with this first one. So it's got a 1 on top. There's nothing that's going to make the top 0. If I look at the bottom, I've got an x minus 4. What number is going to make the bottom 0? Well, 4. And it's a thing that only makes the bottom 0. So we learn out of this that we have a vertical asymptote of x equals 4. Okay. Nothing made the top 0, so that means that there is no x-intercept on this curve. And nothing makes both the top and bottom 0, so there are no holes or points of discontinuity. And that makes sense. If we thought about this graph, it's basically a butterfly moved over. Yeah, it's got a vertical asymptote. All right, the next one. If I want to analyze this, I have to factor it so that I can see its factors. So are there any identical factors on top and bottom? No. You've got an x, and then on bottom you've got an x minus 3 and an x minus 1. You cannot do this. You can't just divide out pieces of the expression. It needs to be whole factors that you divide out. So there's nothing that makes both the top and bottom 0. So that means there are no holes. Okay. What makes just the top 0? Well, 0 would make just the top 0. So a factor of the top is 0. That's going to be an x-intercept. The vertical asymptotes are going to be the numbers that make just the bottom 0. So they would be 3 and x equals 1. So far we have not encountered any holes in our examples. That'll probably change soon, though. All right, this one in C looks like a bit of a mess. That's because it's already factored, but that's actually helpful for you. So, wholes. Are there any factors that are identical on top and bottom? Why, yes, there are. There's these ones here, x plus 1 over x plus 1. So there's going to be a whole, I don't need to use plural, there's a whole at whatever number zeroes that out, at negative 1. Okay, and we're pretty used to that from chapter 3. If we see a binomial of x plus 1 as a number, it probably represents the number negative 1. Okay, what about x-intercepts? What numbers make only the top 0? Well, the number 1 would make only the top 0, so that it's got an x-intercept of 1. What numbers would make only the bottom 0? Those are your vertical asymptotes. Okay. And that would come from x equals 2 and x equals 4. I always give my asymptotes as an equation. All right, so that's really the key information. We can do a weird thing. We can find the coordinates, the y-coordinate of that whole, though it's kind of a silly thing to do. I mean, we're talking about a point where the graph doesn't exist, so it's enough to just say it doesn't exist at x equals negative 1. But you might be interested in, like, what would the y value have been if it could exist? It's a pretty esoteric question, but let's deal with it anyways. How we find that is sub negative 1 for x in a canceled out version of the function. Canceled out version of the function. Because if I just put in negative 1 for x in the original form over here, then I'm going to get 2 times negative 2 times 0. Oh, I'll get 0 on top, but I'll also end up with 0 on the bottom. So I'll get 0 over 0, which is undefined. So instead, what I have to do is cancel out my problems, which seems weird, and then sub them in. And the reason that this is at least sort of okay is because we're not finding a point on the curve. We're kind of finding a non-point on the curve, a place where it would have existed if the curve were defined there. So I'm going to put in negative 1 for x everywhere that x appears. And let's see what I get. On top, I'll get negative 1 minus 1 is negative 2, so I'll get negative 4. And on bottom, I would get negative 3 times negative 5, so that's positive 15. So that's the y-coordinate. So I think we can agree this is a pretty weird function, but it does appear to have vertical asymptotes at x equals 2 and 4. That's good. It does have an x-intercept at 1. And it does have, let's see if we can get it to show up, a point of discontinuity or a whole at negative 1. Oh, it's just barely showing up there. It's undefined. Okay? And it does look like a small negative value, so negative 4/15 makes sense. Desmos, though, thinks it's silly to find that y value. And there's some, valid reason for having that criticism. So C was nice because it was already factored for us. Of course, if it's not factored for us, we just take that one step ourselves. We say, okay, I'll factor the top. I'll factor the bottom. There are probably good reasons to look for wholes first, because you're looking for things that are factors of both the top and bottom. So there's a whole at negative 2, because x plus 2 is a shared factor of the top and bottom. There is an x-intercept at whatever makes only the top 0, so that would be from this binomial, at 2. And there is a vertical asymptote at x equals negative 4 at whatever makes only the bottom, or just this term, 0. So vertical asymptote at x equals negative 4. If we want to find that y-coordinate over here, what we need to do is take sort of a canceled out version of the function. So the function looked like this. And if I want to sub in a negative 4, then or negative 2 rather, I'm going to have to get rid of my problem. I don't like to do this with the original function though, because I'm nervous that, that's not exactly what the original function means. The original function does have a hole. So if I put in -2 for x, what am I going to get? -4 over +2 or -2. So coincidentally, the hole is going to be at -2, -2. Next class, we're going to learn how to graph these, but for now, we're just doing some description. So we can find x-intercepts, vertical asymptotes, and holes, points of discontinuity. The next question in describing rational functions has to do with their end behavior, or what happens to the far right or far left. So I'm wondering whether we're going to get any horizontal asymptotes in these 7 functions. Now you could make some predictions. We're going to head to Desmos and check it out. Here are all these functions. They're not on a 1-to-1 scale. But if I think about what's going on with this function here, this first one, it looks like as I go to the far right and far left, I'm getting closer and closer to the number 2. That is the definition of a horizontal asymptote. You have a horizontal asymptote at x, or at y equals 2, rather. You might say, hold on, it's right on 2. I bet you if you zoom in enough, then it won't be exactly on 2. You'll be able to see that it's a little bit off, and it's getting closer and closer to it. Now, for a horizontal asymptote, you're allowed to pass closer and closer to the value, and you're allowed to pass through the asymptote. But this one is going closer and closer to 2. So this one gets y equals 2. Let's check out the next one. Looks like it's very similar. It's going closer and closer to 5. Next one, you make a prediction. Oh my gosh. What is going on with this graph? Let's see more of it. It does not appear to have a horizontal asymptote. It does kind of have a slanted one. Like as you go out further and further, it's going to look more and more just kind of like a diagonal line. But it does have weird stuff happening in the middle. So it definitely has no horizontal asymptote. It's going off towards infinity on the right, off towards -infinity on the left. No HA. There's a slant one. Let's check out the next. Okay, this one looks like it's getting closer and closer to 0. Even though it clearly passes through on the right-hand side, it's still getting closer and closer to that 0. So we'd say y equals 0, or x-axis asymptote. This one over here, 1 over x, I don't even need Desmos to show me. I know that that's going to be y equals 0, okay, because it's a basic butterfly. Let's check out the next one. Just in case we had any doubt, there's the butterfly. The next one, oh man, it appears to be another one of these slanted ones, so no horizontal asymptote. And while we're here, we might as well grab the last one. And it looks like, I'll have to play with my scale a little bit. Looks like it's closing in on 3, maybe, as we go to the far left and far right. No HA or a slant. This one is going towards y equals 3. So basically we have 3 categories. We have y equals a non-zero number, y equals 0, and y has a slant asymptote. And you could pause and think about what they have in common. But I'm going to mention that all the ones where it's non-zero have equal powers on top and bottom. And as we head out to the far right and far left, they're the only things that are in charge. Okay? They're the only parts of the terms that make a difference, or parts of the expressions that make a difference. And essentially you can just divide them out and you get your asymptote. For the ones where we have y equals 0, they have a higher power on the bottom. And so as we go out towards infinity, the bottom gets a lot bigger than the top, so we head towards 0. And the ones where we have no horizontal asymptote or a slant asymptote, in those ones, the higher power is on the top. So those are the three categories. We look at the drivers, is what I think of them as, the highest powers on top and bottom, and we compare them. Because as we go to the far left and right, they're the only things that are in charge. As a set of fairly concise rules, if you have functions where it's polynomial over polynomial, if the degree on the bottom is greater than the degree on the top, so let's say if you had y equals x squared minus x plus 1 all over 5x cubed plus 2x squared minus 3, all that matters for the horizontal asymptotes is the relationship between this term and this term. Higher power on the bottom means y equals 0 for the horizontal asymptote. If the degree on the top equals the degree on the bottom, then the result of dividing out the drivers is going to be your horizontal asymptote. So let's see. Y equals, let's say we had 3x squared minus 2x plus 5 all over 2x squared plus x minus pi, something like that. In this case, we've got the same power or same degree on top and bottom. The highest power is an x squared. So if we want the horizontal asymptote, here's what we do. We just divide out those drivers. So 3x squared divided by 2x squared would give you 3 over 2. The horizontal asymptote will be 3 over 2, or if you prefer, 1.5. If you graph that function, I guarantee you that will be the case. If the degree on top is larger than the degree on the bottom, there may be a slanted asymptote, or if there's a bigger difference in power, it may be a parabolic asymptote. The main thing is that there's no horizontal asymptote. So let's say, for example, we had y equals 5x cubed plus 3x minus 1 all over x squared minus 5. Highest power is on the top, okay? So no horizontal asymptote. I'll show you how to find those slanted asymptotes when we do one of the examples. But finding horizontal asymptotes is no big deal. You just compare the drivers, or the highest degree, on each of the top and bottom. So find the horizontal asymptotes for each of the following. Let's just identify the drivers. X squared and x squared. Are they the same power? Yes, they are. So divide them out. So take those driver terms. X squared divided by x squared is 1. So the horizontal asymptote will be y equals 1. On the next one, let's find the drivers. It's this and this. Are they the same power? Yes. So that means that we just divide out those drivers, and their coefficients come with them. So 2x squared divided by x squared would be 2 over 1, or 2. This will have a horizontal asymptote of y equals 2. In the next one, let's identify the drivers. The highest power on top is an x. The highest power on the bottom has an x squared. So highest power on bottom, check it out. That's the first case. Degree on bottom is bigger, then y equals 0 is the asymptote. J of y equals 0. And in the last one, the highest power is on the top, so we can say no horizontal asymptote. If you want the slanted asymptote that might exist for this, here's how you find it. You actually do the division. So we're going to take x minus 3, and that'll be what we divide x squared plus x minus 2 by. So I can do long division or synthetic, doesn't matter. X squared minus 3x, subtract, I'm going to get 4x minus 2. And then that's going to give me, when I divide, a positive 4. And then I'll multiply back in. Get this. Looks like I'm going to get a remainder of 10. What that means is that this whole function here could be rewritten as x plus 4 plus some leftovers. And the idea is that as you get closer and closer to infinity, that little fractional part, the 10 over x minus 3, makes less and less of a difference. The curve itself starts to look more just like x plus 4 the closer we go to infinity. And x plus 4 is a diagonal line with a y-intercept of 4 and a slope of 1. I want to show you what that looks like on the graph. So there is that function. Now, we already know it has a vertical asymptote at x equals 3. I'm going to just draw that in, the vertical asymptote. It looks like that. Yeah, it hooks around that. The slanted asymptote that we're going to find is just this piece of the overall function, or just this piece, what we call the quotient, without the remainder when you do the division. So I'm going to graph that on here, y equals x plus 4. Now, they don't look exactly like each other right here, especially if we zoomed in more. If we went here, these functions all look different. The red is the actual function, and the blue and the green are the asymptotes. But the more we zoom out, the more that curve starts to look like its asymptote, which is that green line. It basically behaves like that linear, so it has a slanted asymptote. In general, I won't be looking for you to find slanted asymptotes, but I think it's kind of neat. What's most important is that you can recognize horizontal asymptotes by comparing the drivers. If it's same power on top and bottom, divide them out. If it's highest power on bottom, then the y equals 0 or x-axis is your horizontal asymptote. That's shown in color here. You can take a look at the practice sheet for describing rational functions. It's just going to ask you for the x-intercepts, all the asymptotes, and any holes that exist. Tomorrow we'll look at actually graphing some of these. I hope this has been helpful. Good luck with the material, folks, and take care.